on to chapter 7 now. This is all about similarity. So today's will be more like an introduction to similarity, if you will. Um, it's not the same thing as congruent, and that's the main thing that you need to come out of this. Okay? So here's your definition right here: two figures that have the same shape but not necessarily the same size. So if they're congruent, they have the same size. But if they're similar, they just look the same, but they're not the same size. Picture like Mini Me from Dr. Evil. Mini Me is similar to Dr. Evil, but they're not the same thing. They're not congruent. That's what similar is. Okay? So, two things that make them similar: their corresponding angles are congruent. The angles have to be congruent in order for the shapes to be the same, with quotations around same. Okay? And then the corresponding sides are proportional. So they're in some sort of a ratio, a 1 to 2 ratio, a 3 to 5 ratio, something like that. The similarity ratio is the ratio of the lengths of the corresponding sides. So that tells us how similar they are. Okay? So right here in this problem, you see this little, it's called a tilde in Spanish, but this means similar. So anytime you see that, they're not equal, they're similar. Okay? So they tell us that these two shapes down here at the bottom are similar. And so we're going to complete these two statements. It says measure of angle E. I want to know the measure of this angle. Well, we know if the shapes are similar, then their angles have to be the same and their angles have to match up. So E matches up with A, and A is 53 degrees, so that means that E also has to be 53 degrees in order for this to work. Alright? And then this proportion, this is one of those things that you guys always tell me to cross multiply and divide kind of thing. So they're saying that AB is proportional to EF, so AD is proportional to EH, is how we would finish that out. Okay, and then we could set up a cross multiply problem out of this. Alright, we need to decide if these triangles are similar. So first thing, you have to figure out how they match up, and then figure out if their sides are proportional. See how all of their angles, there's a 1 arc, there's a 2 arc, there's a 3 arc on each triangle. So that means their angles are congruent already. So we know that's the first step. Second step would be to match up the sides. So this 20 matches up to the 15. Okay, so 15 over 20, that reduces to 3/4. Okay, let me grab a different color. And then the 12 matches up to the 16. So we put 12 over 16 and reduce that, and that's also 3/4. And then the 18 matches up with the 24. Go 18 over 24, and that also reduces to 3/4. So these two shapes are similar by this information. So the similarity statement, we say triangle ABC is similar to triangle, and we have to match everything up. So this would be FED. And then their similarity ratio, we'll put SR equals 3/4 because that's the ratio that all the sides were in. Okay? So those two triangles are similar by a ratio of 3/4. Alright, this one they also tell us that they're similar by the similarity statement. We want to find the value of x up here. So we start matching sides up. We say 2 matches up with the x. There's a 3.2 here, but it doesn't match up with anything, so that doesn't help. And then 5 matches up with 6. So we can put 2 over x equals 5 over 6. And we can solve. Cross multiply and divide by 5. And we get x equals 12 over 5, or 1 and 2 2 and 2/5, sorry, or 2.4, however you want to say it, whatever we need for the problem that we're working on. Alright, there's also this thing with similarity called the golden ratio, and this actually is in art, it's in architecture, it's in nature, it's all over the place. It's pretty cool. There's a thing called the golden rectangle, and this is a rectangle that can be divided into a square and a rectangle that's also similar to the original rectangle. I'll show you a picture of this. And then the way the rectangle is split is in the golden ratio, which is approximately 1.618 to 1 is the ratio. So that could be a fraction. You could write it 1.618 to 1. Okay? Anything that's set up in the golden ratio, they've done studies on this, and most people consider it to be pleasing to look at. They're beautiful to see. Everything is symmetrical, whatever. So it looks well to the eye. And Leonardo da Vinci was the artist that really was kind of a pioneer in this and kind of used this in his paintings. And probably the most important painting that you guys have seen is the Mona Lisa, which we'll look at here in a minute. Okay, so here's what the golden rectangle looks like. It's a rectangle that gets split into a square and a rectangle that's similar to the original one by the ratio of 1.618 to 1. And then that rectangle can be split into a square and a rectangle that's also similar to the original rectangle. And it just keeps going. And so you draw this spiral from diagonal to diagonal. And it continues. And it literally should keep going forever. If you could zoom in on this center piece right here, it would keep going forever. Okay, so anything that's set up in this spiral is considered to be pleasing to look at. Like all of these. Okay, here's the Mona Lisa, and they figured this out by just superimposing the golden rectangle onto her face. They started studying things, trying to figure out why everybody thought she was so beautiful to look at. And so they figured out this ratio. Well, then it turns out there's other things in nature that can do the same way. There's waves that go in the spiral, there's roses, there's nautilus shells, there's hurricanes, there's all kinds of stuff. Buildings, you name it. Okay, it's kind of called a Fibonacci spiral if you see that, but these are considered to be pleasing to the eye. Okay, so there's a little geometry in art or in nature. Alright, let's do a word problem with this just to make sure we got it. So we have this artist that plans to paint a picture. He wants the canvas to be a golden rectangle with its longer horizontal sides 30 centimeters wide. So if they tell us longer horizontal sides, then that means the canvas is going this direction. And the longer horizontal sides are 30 centimeters. Not real big, but it's there. And they want to know how high the canvas should be. Well, we know the golden ratio is 1.618 to 1, and this is longer side to shorter side. So from our canvas, we would do longer side over shorter side, and we would cross multiply and divide like we're used to. So you take 1 times 30, and then 1.618 times x. So you're going to take 30 divided by 1.618. So the canvas should be 18.5 centimeters tall. Okay? Nothing real intensive yet, but we're going to get there. A lot of ratios this chapter.